Okay, so in this lesson we're going to start solving exponential equations, and we're going to do these problems. We're going to solve these exponential equations in which the bases are going to be the same. In the next lesson, you're going to see how to solve them when the bases cannot be the same. Now, an exponential equation is an equation containing variables in the exponents. So that's what an exponential equation is. Remember, an exponential function, remember the exponential function, f of x equal b to the x. Remember, that's an exponential function. Exponential function. So we talked about that in previous lessons. So an exponential function is a function in which the variable is in the exponent. So an exponential equation is an equation in which the variable is in the exponent. So here's some examples. Something like 2 to the 2x minus 1 equals 6. So notice the variable is located in the exponent. Another example might be something like 5 to the x equals 17. So notice the variable is located in the exponent. We could have 2 times e to the x minus 1 equal 6. Things like that. Or 6, let's say, e to the x. So you can have variables on both sides as long as the variable is in the exponent. All right, so those are all examples of exponential equations. Now the idea in this lesson and the next lesson is to solve exponential equations. All right, so we're going to solve for the variable x. Okay, so let's first of all talk about the one-to-one property for exponents, and that's what we're going to use in this lesson. It's called the one-to-one property for exponents. It's a very simple property. For example, you've used it before. So suppose we had 2 to the x is equal to, let's say 2. Let's say 2 cubed. Okay? So this right here involves the one-to-one property for exponents. So basically, you see this exponential equation? What do you notice about the bases? Well, you notice the bases are the same. Well, in order for this side right here, the left side, to equal the right side, what do you think this x, the value of x must be? Well, the value of x must be 3. So if the bases are the same, then the exponents have to be the same, hence the one-to-one property. So this x has to equal that exponent. So this exponent has to equal that exponent. So if the bases are the same, remember this one-to-one property only applies if the bases are the same. So if the bases are the same, then the exponents have to equal. So therefore x must equal 3. Kind of makes sense because 2 to the third is equal to 2 to the third. Okay? So the one-to-one property basically says this. If you have b to the m equals b to the n. So if the bases are the same, then the exponents have to be equal to each other. So I'm going to say this. If this is the case, then m must equal n. Okay? All right, so let's do some examples with this. So we're going to solve. Now the directions will say this. So you must read the directions carefully. Always read the directions. The direction says solve each equation by rewriting the bases as needed and applying the one-to-one property of exponents. Okay, so let's start with a simple example. So we're going to solve each. So let's look at the first one. So let's suppose we had 2 to the x is equal to 64. 2 to the x is equal to 64. Now remember, the direction says they want you to use the one-to-one property for exponents. Now the one-to-one property says, first of all, before you can say the exponents are equal to each other, the bases must be the same. So if you look on the left side here, that base is 2. So our goal is to somehow get to rewrite 64 as 2 to a power. Okay? So we need to rewrite 64 as 2 to some power. All right, so you got to figure out what that is. All right, so let's think about 2 to the third. Is 2 to the third equals 64? No, 2 to the third, remember, is 2 times 2 times 2, which is 8. All right, what about 2 to the fifth? Well, let's say 2, so that's 2 cubed times 2 squared, correct? So we already figured out that 2 cubed is 8, and 2 squared is 4, so that's 32. So we're almost there. All right. So that's 2 to the what? The 5th, we said? Okay, so that's 2 to the 5th is 32. So what about 2 to the 8th? Let's figure out what that is. I'm sorry, 2 to the 6th, excuse me. 2 to the 6th. Well, 2 to the 6th is 2 to the 5th times 2. So that's 32 to the 5th, remember, is 32. 32 times 2 is 64. So 64 is 2 to the 6th power. All right, use your calculator if you need to. So just use your calculator. Keep figuring it out. So, I mean, I did it the long way. I did it the long way without using a calculator. But the point here was just to remind you how to deal with exponents. So use your calculator. Keep doing this, all right? So let's try, remember I'm trying to get 2 to a power. So let's see. 2 raised, no, I'm raising it to the 3rd. Let's do 3rd. So that didn't work. Then we said 2 raised to the 5th. That doesn't work. Then we said 2 raised to the 6th. There we go. That's 64. All right, so use your calculator. You have a calculator here. All right, now remember, you must show this step. You must show this step. It says rewriting the bases as needed. So you must show this step. So you got to show this. And now you use the one-to-one property. So instead of writing out the letters O-N-E, I'm just going to say one-to-one like this. So one-to-one, I can say one-to-one property. So if the bases are the same, the exponents are equal. So therefore, the solution is x equals 6. There's your answer. All right, number 2. Let's look at another simple one. Suppose we had this. Suppose we had 5 to the x equals 125. 5 to the x equals 125. All right, so notice that base is 5. Is there any way I can rewrite 125 as 5 to a power? So that's your goal. So your goal is this. Is there any way I can rewrite this as 5 to a power? So use your calculator to think about it. 5 squared is 25. 5 cubed is, there you go, 125. So it's 5 cubed. Now, can you use the one-to-one property? The answer is yes. Since the bases are the same, these exponents have to equal. So x must equal 3. Number 3. Okay, now, suppose we had this. Suppose we had 2 to the 2x minus 1 is equal to 32. 2 to the 2x minus 1 is equal to 32. All right, so that base is 2 right here. See that 2? So is there any way I can rewrite 32 as 2 to a power? So is there any way I can rewrite 32 as 2 to a power? So let's see. 2 raised to the 5th power is 32. There you go. 32, 2 to the 5th. All right, now, you see how it was simple here? And the reason why we went, these two problems here, the first two were simple, is because this exponent here was already x. So x equals 6, x equals 5. Here that's not the case. So there's just a little bit more work you're going to do. So you have to say, using one-to-one property, since the bases are the same, you now have to say this. You have to say 2x minus 1 must equal 5. All right, so you got to show this, and you got to show this, and you got to solve. Okay, so make sure you understand what needs to be shown. So you show the bases being the same, then you set the exponents equal to each other, and then you solve. Now notice what kind of equation is this? So I went from an exponential equation to a linear equation. So this is exponential. I went from an exponential equation to a linear equation. And now you just got to solve this linear equation. So we're going to add a 1 to both sides. So I get 2x equals 6. And so therefore, if I divide both sides by 2, I have my answer. The answer is 3. So x equals 3. And you can check it. I mean, check it real quick. Look, this is what you do. 2 times 3 is 6. 6 minus 1 is 5. 2 to the 5th is 32. You're done. That's it. All right, the next one. It's not that bad. All right, number 4. Suppose we had this. 4 to the 2x minus 1 equals 64. 4 to the 2x minus 1 equals 64. Okay, now there are a couple ways you can do this. I want you to think about this for a moment. In all the ones we've done, you see this base was 2, so I rewrote this with base 2. You see this base was 5, so I rewrote this with base 5. You see this base was 2, so I rewrote this with base 2. Okay? See this base is 4. So what you're probably thinking is, all right, this base is 4, so let's see if I can rewrite this as 4 to a power. Okay, let's think about that. So let's just try. Can I fill in this box right here? So let's see. 4 squared is 16. 4 cubed is 64. So I can. So right away I can rewrite the 64. I can use this base. See, this base is 4. So always your question is, can I rewrite this number using the same base? And the answer is yes. So right away I can say this. 4 to the 2x minus 1 equals 4 cubed. Okay? So again, you must show this. You have to show this. You must show this. And now, notice how I'm going to use the one-to-one property for exponents now. We're now using the one-to-one property for exponents. And so basically it says this: if the bases are the same, the exponents have to be equal to each other. So 2x minus 1 must equal 3. And notice I went from an exponential equation to a linear equation. This is linear. And then you just solve this linear equation. So you're going to add 1 to both sides. You get 2x equal 4. Divide both sides by 2. And you get x to be 2. And so there's your answer. So your solution is 2. And you can check. 2 times 2 is 4. 4 minus 1 is 3. 4 cubed is 64. All right. Now, here's what I want to show you, and that's going to be important. Well, actually, let's come back to this when we get to it. So let's look at number 5. So we're good here. Let's just go on. So look at number 5. All right. Suppose we had this now. Suppose we had this. Suppose we had 32 to the x is equal to 8. Okay, now it's starting to get a little bit more challenging. Because in the previous four problems, it was very easy to get the bases to be the same. I just used whatever base was on the other side, and I just rewrote the other side using that same base. But here's the problem. You have 32 and 8. First of all, if you say, well, I'm going to get the bases be 32. Okay, always think like that. All right. So can I get the bases be 32? So in other words, can I write 8? Can I write 8 as 32 to a power? That's the question. And this power we want to be a whole an integer. An integer. So is it possible? No. Okay. So no integer works. No integer works. Okay, so then your question may be this then. Your question may be, well, can I get the bases to be 8? Can I get the bases to be 8? All right, can I get the bases to be 8? All right, so let's think about that. So is there a way you can rewrite 32 as 8 to an integer power? For instance, 8 squared is 64, so no integer works. So this is a little bit more challenging. There's no way you can get the bases to be 32, and there's no way you can get the bases to be 8. So here's the idea. It is usually best if you think about prime numbers. Okay, think about your prime numbers. My prime numbers are 2, 3, 5, 7. 8's not a prime number, 9's not a prime number, 10's not a prime number, 11, 12, 13, 14, 15, 16, 17, and so on. Those are your prime numbers. Okay? It turns out that see that 32 and 8, those are composite numbers. In a previous course, you learned that every composite number can be written as a product of prime numbers. Every composite number can be written as a product of prime numbers. Okay, now what that means for us is this. My first prime number is 32. The question is this: can I rewrite 32 and 8 as 2 to a power? And the answer is yes. Okay, so you want to use 2. So for example, the easiest one is 8. 2 to the third power is 8. Do you see that? 2 to the third is 8, so I'm going to use 2. Now 32. Do y'all see, I'm going to write this right here, do y'all see that 32 is 2 to the, and let's check this, 2 to the fourth is 16, 2 to the fifth is 32. I'm sorry, 2 to the fifth is 32. Alright, so I'm going to rewrite 32 as 2 to the fifth. Now be careful. That's just 32, but what are you doing to that 32? You're raising the x power, so you got to say this. So here's what you got to see now. This 32 is 2 to the fifth, but that 32 is being raised to the x power, so you got to put that in parentheses and raise to the x power. This 8 is 2 cubed. Okay, so remember what we did here. First of all, we asked ourselves, can I rewrite both of those with bases 8? No. There's because you want to use integers as your exponents. So the answer is no. Can I rewrite both of those as base 32 with integer exponents? The answer is no. So then we're going to use the fact that every composite number, 32 and 8, are composite numbers. Remember, a number that's prime, and a number that's not prime is a composite number. That's what a composite number is. So these are prime numbers, and there are an infinite number of them. All the others are composites. So all these composite numbers can be written as a product of prime numbers. So ask yourself, what prime number can I rewrite 32 and 8 as? So if you try 2, 8 is 2 cubed, and 32 is 2 to the fifth. Okay? Now we're going to use this. Remember last semester, semester before that, and even in this course, we talked about this. A power raised to a power, so use a power rule. A power raised to power, you multiply exponents. So this is 2 to the 5x equals 2 cubed. And now notice, so I got rid of the parentheses, you got to get rid of the parentheses. So you now notice that the base is the same, so the exponents have to be equal. So 5x must equal 3. To get x by itself, divide both sides by 5. You get x to be 3/5. So that one was challenging. We're going to look at another one, and it will get a little bit easier. Come back to this, though, and look at this lesson again. All right, but let's look at number 6, and it will get a little bit better. You'll understand it will get a little bit better as we go through this. Okay, number 6. All right, suppose we had this. Suppose we had 9 to the x plus 2 power equal 27 to the x minus 1 power. All right, don't make it difficult. It's not that difficult. All right, so what you want to do, remember, is get the base to be the same. Now, do not make the mistake and say those exponents have to equal to each other. That's not true. The one-to-one property for our exponents only apply if the bases are the same. Are the bases the same? The answer is no. Only applies if the bases are the same. So what we got to do now is rewrite these bases with the same base. So the question becomes, and you should always use the smallest So if you want to try 9 and 27, oh, you've got to always use the smallest one here. So can I rewrite 27 as 9 to a power, 9 to an integer? Can I rewrite 27 as 9 to an integer? And the answer is no. So let's think about our prime numbers. What prime number do you think will go into 9 and 27 at the same time? The answer is 3. 3 will go into 9 and 3 will go into 27. So here's what you want to do. You think of this first. 9 is 3 to what power? And 27 is 3 to what power? That's what you got to think of. Well, 9 is 3 squared and 27 is 3 cubed. So now you're going to rewrite this 9 and 27 using these bases, base to a power. So here's what you do though. Be careful. You're gonna rewrite the 9. Remember, oops. You're gonna rewrite the 9 as 3 squared, but that's being raised to the x plus second power. So notice the parentheses. You have to do parentheses. You have to put those parentheses in there. 9 is 3 squared, but remember, that's also being raised to the x plus second power. Equal 27 is 3 cubed in parentheses, but that's also being raised to the x minus 1 power. Those parentheses are necessary. And again, you got to show this. You must show this. These are your steps. Now remember the properties we learned about power rule. A power raised to a power, you multiply. Now you got to be careful. All of this is being multiplied by 2. So now we get this. We get 3 to the 2x plus 4. Make sure you see this. All of this is multiplied by 2. Power raised to power, you multiply. 2 times x is 2x. 2 times 2 is 4. Okay? Equal. Same thing here. Power raised to power, you multiply. So that's the base is 3. 3 times x is 3x. 3 times a negative 1 is a negative 3. So that's where we're at. All right, so that's your thinking processes. I have to get the bases to be the same. So you got to think, well, what base can I use? So for 9 and 27, the prime number that goes in 9 and 27 is 3. Okay? Now notice, can I use the one-to-one property here? Can I use the one-to-one property? The answer is yes. Because the bases are the same, those exponents have to equal. So 2x plus 4 has to equal 3x minus 3. And notice I went from an exponential to a linear equation. This is now linear. And so I can solve this linear equation. So I'm going to subtract 2x from both sides. Combine like terms, I get 4 equals 3x minus 2x is x minus 3. Add 3 to both sides, I get x equals 7. So x equals 7. All right. So quite a bit of, it's a little bit more challenging, quite a bit of work as you go along. So let's look at number 7. So number 7, suppose we had this in number 7. Suppose we had 5 to the 3x minus 6 is equal to 125. Okay, now notice this base is already prime, right? That's a prime. So if you go back to all the others, you'll notice something when you go back. This base was prime. This base is prime. This base is prime. Now here, though, this base is not prime. But we notice that 64, I can still write using this base. Even though it's not prime, it's okay, because I can write 64 is 4 cubed, I can get it right away. But you could have rewritten this using a prime number. All right, and we're gonna do that one again, but you could have. So notice this is prime, so you're gonna ask ourselves, well, is there any way I can write 125 is 5 cubed? And the answer is, is there any way I can rewrite 125 as 5 to a power? And the answer is 5 cubed. So I got 5 to the 3x minus 1 equals 5 cubed. And now I can use the one-to-one property. So these exponents must equal each other. So 3x minus 1 must equal 3. Adding 1 to both sides, I get 3x equals 4. And then divide both sides by 3. I get x to be 4/3. So there's your answer. But what if I had this? What if I had this problem? Let's say I had 5 to 3x minus 6 equals 125 to the 2x. Let's make that 2x. 2x plus 7. Suppose I have that. Okay. So the same basis, except I have an exponent here. Well, the base here is prime, so I need to figure out how can I rewrite 125 as 5 to a power. Well, we just saw it's 5 cubed. So here's what you're going to do now. You're going to say 5 to 3x minus 6 equal, now 125, you're going to write as 5 cubed in parentheses. The parentheses are necessary because that 3 is going to be multiplied by that 2x plus 7. Remember, this 125 is being raised to this power. So that parentheses is necessary. You must write it. And now you're going to use the power rule. So you're going to multiply these two powers together. So I get 5 to the 3x minus 6 equals 5. Now 3 times 2x is 6x. 3 times 7 is 21. So that's what I get. So remember, you're saying 3 times 2x plus 7. So you distribute. And that's how you get this. And that's how you would get all the others as well. And now I'm going to use the one-to-one property. Use the one-to-one property. And so these exponents must equal since the bases are the same. So 3x minus 6 must equal 6x plus 21. And notice I went from an exponential equation to a linear equation. And I'm just going to bring all the variables one side, constants to the other, just like I've been doing. So I'm going to subtract 3x from both sides. So I get, combine like terms, that's 0. So you get a negative 6 equals 6x minus 3x is 3x plus 21. Subtract 21 from both sides. Combine like terms. That's going to be a negative 27 equals 3x. Divide both sides by 3. I get x to be a negative 9. So that's your solution, negative 9. Okay? Alright, number 9, let's suppose we had this. Alright, number 9, let's suppose we had 8 to the x plus 2 equals 4 to the x minus 3. So 8 to the x plus 2 power equals 4 to the x minus 3rd power. Alright, so first of all, realize that there's no way I can rewrite these bases as 4s. Because 4 is not 4 raised to an integer power. 4 squared is not 8. 4 squared is 16. So now you got to go and think about, well, what prime number can I use? What prime number can I use for 8 and 4? So 8 and 4, let's use the prime number 2. So 8 is 2 cubed and 4 is 2 squared. So my bases are going to be 2's. That's what I'm going to use. I'm going to use base 2. Base 2. So 8 is 2 cubed, but remember, you're going to put that in parentheses. So circle it and say, I've got to put that in parentheses. And then that's being raised to the x plus 2 power. And over here, this 4 is 2 squared, but in parentheses, because this exponent 2 is being multiplied by this exponent x minus 3. So again, you got to show this. You must show that. And now let's use our power rule. When you have a power raised to power, you multiply. So basically you're saying 3 times x plus 2. That's what you're saying. And then you distribute, you get 3x plus 6. So this becomes 2. Now you didn't have to write this. In your mind, you could have said 3 times x and 3 times 2. But mistake some people make is they only do the first one and say that's 3x plus 2. It's not 3x plus 2 now. It's 3x plus 6. So both of these have to be multiplied by 3. So you always have to be careful. Same thing here. That's really 2 times x minus 3, meaning this. And so distributing, you get 2x minus 6 here. So that's 2 to the 2x minus 6. Alright, now since the base is the same, I can use the one-to-one property now. Use the one-to-one property. So these exponents must be equal. So 3x plus 6 must equal 2x minus 6. So notice I went from an exponential to a linear. So I'm going to solve this linear equation. Remember, that's linear now. And so I'm going to bring the variables to one side. So I'm going to subtract 2x from both sides. 3x minus 2x is x, plus 6 equal, that's 0, a negative 6. Subtracting 6 from both sides, I get x to be negative 12. That's what you get, negative 12. Okay, let's look at this one. All right, suppose you had, let's say you had number 10. Let's say you had 8 to the 2x minus 1 equal 16 to the 4x plus 3. 8 to the 2x minus 1 equals 16 to the 4x plus 3. All right, so what base do you think you're going to use? The bases are different, so be careful. The bases are different, so don't say 2x minus 1 must equal 4x plus 3. That is not true. You have to get the bases to be the same in order to use the one-to-one property about exponents. So now, if you use 2, if you want to use 2, that works because 8 is 2 cubed and 16 is 2 to the 4th. Okay? Now, let's use 2 for right now. So we're going to use base 2. So we're going to use base 2. So 8 is 2 cubed, and that's being raised to the 2x minus 1. 16 is 2 to the 4th, and that's being raised to 4x plus 3. So notice the parentheses. And the parentheses are necessary. Remember, the parentheses are necessary because this exponent is being multiplied by this exponent. Hence the power rule. The power rule. So here, remember what's happening in your mind. You're saying 3 times 2x minus 1, and then you distribute, and you get 6x minus 3. So you didn't have to write this. You can just thought about it. 3 times 2x is 6x. 3 times negative 1 is negative 3. So this is 2 to the 6x minus 3. Equal, same thing here. Power raised to power, you multiply. Notice the parentheses were necessary. They were necessary. You must write them. So 4 times 4x plus 3, distribute, you get 16x plus 12. That's what this is. So that's 2 to the 16x plus 12. And now, notice, again, you got to show all this. You must show. Show. Those are your steps. So now, I can use the one-to-one property. So the one-to-one property says if the bases are the same, the exponents have to equal. So 6x minus 3 must equal 16x plus 12. And now notice I went from an exponential to a linear. So I'm going to subtract 6x from both sides. So bring all the variables to one side, constants to the other. That's how you solve a linear equation. So I get negative 3 equals, that's what, 10x plus 12? Subtracting 12 from both sides, I get negative 15 equals 10x. I'm going to go ahead and rewrite it here. Getting x by itself, you can divide both sides by 10. And so I get x to be negative 15 tenths, which reduced is negative 3 halves. So that's x. So x is negative 3 halves. All right, so notice what I did was I used base 2. Now, here's what I want you to see. Now, remember, you always resort back to a prime number. But I want you to see this. I'm going to write this as 10 again. We had 8 to the 2x minus 1. Actually, no. Okay, so we're good with this one. What I want to do is go back to, let's see where it was. Okay, this one here, number 4 is what I meant. So let's go back to number 4. Number 4. So number 4, we use 4 as the base. If you want to use a prime number, what prime number can you rewrite 4 and 64 as? The answer is 2. So let's do 4 using base 2, just so you get the same thing. So we write the problem. Okay, so using base 2, do you agree that 4 is 2 squared? 4 is 2 squared, so that's 2 squared to the 2x minus 1. Do you agree that 64 is 2 to the, and if you can't figure out right away, use your calculator. Use your calculator. So 64, let's see, is, all right, 2 raised to the 5th power. Is that 64? No. 2 raised to the 6th power. Is that 64? Yes. So I can rewrite 64 as 2 to the 6th. So I get 2 squared to the 2x minus 1 equals 2 to the 6th. Okay? Now go ahead and use your power rule here. So you can multiply this out. So you're saying 2 times 2x minus 1. That's what you're saying. And that's going to equal, you distribute, you get 4x minus 2. That's what you get. So this right here becomes 2 to the 4x minus 2 equals 2 to the 6th. Okay, so when you have a power raised to power, you multiply. That's how we get this. So notice my base is the same now. Base is 2. So therefore I can use a one-to-one property. So it says the one-to-one property for exponents. So it says that these exponents must equal. So 4x minus 2 must equal 6. Okay? And so notice I went from an exponential equation to a linear. So I'm going to add 2 to both sides. So I get 4x equal 8. Divide both sides by 4. I get x to be 2. And notice that's the same answer we got when we used the base 4. Remember that? So I get x to be 2. You get the same answer. All right? Okay, so let's try and do one more with this. So let's do number 11. Let's see. Number 11, let's say we had, okay, let's do this one. Let's say we had e to the 2x plus 1 equals, all right, now be careful with this, 1 over e to the 5x minus 3. That one's a little bit challenging, but let's think about our discussions from previous lessons. Okay, now don't make the mistake and say that the bases are the same. The bases are not the same. The bases are not the same. This base is e. This base is 1 over e. E does not equal 1 over e. Okay? That's not true. So those bases are not the same. You can even put that in your calculator. E is approximately equal to 2.72. 1 over e. If you do 1 over e, 1 divided by e, I gotta get e now. You gotta press second e to the first power. That's 1 over e. Is about 0.37 to 2 decimal places. So notice they're not the same. So don't think those bases are the same just because you see an e. You got to think about the base. This base is e. This base is 1 over e. Okay? All right, but remember the previous lesson or one of the lessons before. Do you remember that 1 over e? If you want to rewrite this in the numerator, then remember this is 1 over e to the first. So do you remember that becomes 1 over e becomes e to the negative 1? So when you rewrite the a term like this with a power in the numerator, or when you bring it to the denominator, the sign of the exponent changes. So 1 over e to the first is e to the negative 1. So what you want to do is rewrite this right side as e to the negative 1 in parentheses. So 1 over e is e to the negative 1, but that's being raised to the 5x minus 3rd power. And so now, so I'm going to rewrite the left side, so that's e to the 2x plus 1. Okay, now remember, when you have a power raised to power, you multiply. So this really becomes negative 1 times 5x minus 3. So now you're distributing. So that's negative 5x plus 3. So this becomes e to the negative 5x plus 3. So the challenging part here was remembering that 1 over e is really e to the negative 1 power. And now you have the bases to be the same. See, base e, base e. Okay, now remember, e to the negative 1, you're still raising them to the 5x minus 3. So when you have power raised to power, you multiply. So negative 1 times 5x is a negative 5x. Negative 1 times negative 3 is a positive 3. So now I can use the one-to-one property. So when the bases are the same, I set the exponents equal to each other. So 2x plus 1 must equal negative 5x plus 3. And so I solve this linear equation. So I'm going to add 5x to both sides, just like this. Combine like terms, I get 7x plus 1 equal, that's 0, 3. Subtract 1, I get 7x equal 2. And then divide both sides by 7, I have the answer. My solution is 2 sevenths. That's my solution. Alright, let's do one more. Let's try this one. Suppose I had this. Let's see, let's make this 12. Alright, suppose I had, let's see, 25 to the 3x minus second power equals, let's say, 5 to the x plus 2. Alright, well, that one's not too difficult because this is already a prime number. So I can rewrite 25 as 5 squared, right? So I'm going to rewrite this. This is prime. I can't do anything with it. So 5 squared to 3x minus 2. Make sure you put that in parentheses. And that's equal 5 to the x plus second power. So when you have a power to raise to power, remember you're going to distribute here. So you got to multiply these powers, these exponents. So that's 5. 2 times 3x is 6x, and 2 times negative 2 is negative, 6x minus 4. Okay, equal 5 to the x plus 2. So now I can use a one-to-one property because the bases are the same. So the bases are the same, the exponents must equal. So 6x minus 4 must equal x plus 2. And now I went from an exponential to a linear. So I'm going to solve this linear equation. So bring the variables one side, constants to the other. So I subtract x from both sides. I get 5x minus 4 equal 2. Add 4 to both sides. Combine like terms. I get 5x equal 6. And divide both sides by 5. I have my solution. So my solution is 6 fifths. So that wasn't difficult. Let's do 13. Let's suppose we had this. Let's suppose we had 9 to the x minus first power equal, let's say 81. Oops. Yeah, let's say 81. 81 to the 3x minus second power. That'll be fine. Okay, so let's think about this. All right, so now the bases aren't the same, right? So the bases are different. But I want you to notice something. See how this is a 9? You may think, well, I can leave this as 9 because I can write both bases as 9. That is true. You can. You can because 81 is 9 squared. So the question becomes, do you have to use a prime number for your base? No, you don't. You do not. So you could leave it as 9 for your bases. The issue was, I think, though, when you came to, if I can find it, was here. See right here. So this is 8, this is 4. There was no way you could have gotten the bases to be 4. There was no way you could have gotten the bases to be 8. So you had to use a prime number 2. Here, though, here, 81, I can write as 9 squared. So you don't always have to use prime numbers down here for your bases. The only time you do, the only time you have to is if there's no way you can rewrite one of the bases using the other. See, I can write 81 as 9 squared. Here, if I can find it again, there was no way I can write 8 as 4 to an integer power. So I had to resort to base 2, like we did here. So what you may want to do is this. You're going to say, okay, I'm going to write as base 9 then. So that's 9 to the x minus 1. I'm going to write 81 as 9 squared, okay? And that's 3x minus 2. And now I'm going to use the power rule here. So I have 9 to the x minus 1 here, equal, so remember you're going to multiply exponents, so that's 2 times 3x minus 2, and then distribute, that's 6x minus 4. So that's 9 to the 6x minus 4. And now the bases are the same, so now I can use a one-to-one property for exponents that says these two exponents must equal each other. So I end up with this equation. And notice this is a linear equation, so I'm going to subtract x from both sides, Combine like terms. X minus x is 0, so I get negative 1 equal 6x minus x is 5x minus 4. Adding 4 to both sides, negative 1 and a positive 4 is 3, so I get 3 equals 5x. And dividing both sides by 5, I found the solution. The solution is 3/5. Okay? Now, I want to go back to the same problem. I'm going to ask you, if you did not recognize that 81 I can write as 9 squared, or that I can use base 9, if you didn't recognize that, then what prime number would you have used? Because they're composite, okay? And both of those composite numbers have the same. Both of those now have the same prime factor. Both of those have the same prime factor. So what would you have used? Well, you would have used 3. So let's use 3. So let's do 13 again. Let's do 13 again, just to see what you would do. And let's use the base 3. So let's use base 3. Because both of those composite numbers have 3 as a factor. Okay, so 9 is 3 squared, right? So I'm going to rewrite this 9 as 3 squared, but is being raised to x minus 1, so make sure you put that in parentheses. 81 is 3. Now, if you're not sure what it is right off the bat, just use your calculator. So 3 raised to the 3rd power is 27. 3 raised to the 4th power is 81. So 3 to the 4th. So 81 is 3 to the 4th, and it's being raised to 3x minus 2nd power. And now you're going to use your power rule. Use your power rule. So you're going to multiply these powers together. You're going to multiply these powers together. If you can't do this in your mind, if you can't say 2 times x and 2 times negative 1, then write it out. You're saying 2 times x minus 1. That's what you're saying. This power times this exponent times this exponent. But you need parentheses here. And distribute, you get 2x minus 2. So this becomes 3 to the 2x minus 2. My base is 3. Equal, and this is going to be 3 to some power, so we got to figure out what that exponent is. So that's 4 times 3x minus 2. And then distribute, I get 12x minus 8. That's what this is. So 3 to the 12x minus 8 power. And now can I use the one-to-one property? And the answer is yes. Why? Because the bases are the same. So since the bases are the same, I can now say that these exponents must be equal to each other. And what kind of equation is this? This is now linear. So it's easy to solve a linear equation. Bring all the variables one side, constants to the other. It is easier to bring the variables to the right-hand side. So I'm going to subtract 2x from both sides. Combine like terms, 2x minus 2x is 0. I'm left with the negative 2 equal 12x minus 2x is 10x minus 8. Adding 8 to both sides and combining like terms, a negative 2 and a positive 8 is 6. A negative 8 and a positive 8 is 0. I'm left with 10x. And then to get x by itself, I am going to now divide both sides by 10 and reducing. They're both divisible by 2. I get 3/5, which is what I had when I used base, right here, when I used base 9 instead. I still had 3/5. Okay, guys, that's going to be the end of this lesson. It's not a difficult lesson. So in this lesson, remember, you got to follow the directions. The directions said you must solve these equations, these exponential equations, by using the same base and using the one-to-one property. So in each of these, you have to use the same base. Okay?